In this screencast, we work a series of examples involving linear functions. We begin with example 8.2. Suppose the depth of a river during spring melt is rising at a constant rate of 1.5 inches per day. Currently, the river is 8 feet deep at its deepest point. Determine an equation for the function that calculates the depth of the river at any time, and then sketch a graph of your function. Be sure to label your axes. So we want to find an equation for this function. Every function has two variables, an input variable and an output variable. For us, it's time measured in days since the present day, and the depth of the river measured in inches, say. So let's let t represent days since the present, and let's let d represent the depth of the river. And let's do it in inches. Okay, first question. If we're going to create an equation for this function relating these two variables, what kind of equation should it be? Is it linear? Well, you are told that the depth is rising at a constant rate of 1.5 inches per day. Since the depth is growing at a constant rate, that suggests that the depth is growing linearly. So a linear equation would be appropriate for this situation. Every linear function has the form y equals mx plus b. We need to fill in each of the four parts of this function, namely the y, the m, the x, and the b. We have to fill in each part with the part that's relevant for this example. First of all, the x, that's our input variable. That's being played by t in this case, and y, our output variable, that's the depth. B, that's our initial amount, which in this case would be our initial depth, or our current depth, which is 8 feet. So 8 feet, given in terms of inches, let's see, we can do this down here. So B is our initial depth, that's 8 feet, but we want to determine what this is in terms of inches, so I multiply by 12 inches per foot. Notice that cancels out the feet and I'm left with inches, and if I do the multiplication I arrive at 96 inches. So the B is 96. Finally, the m, that's the rate of change. You're told that the depth is rising at a rate of 1.5 inches per day. Since the rate is already given in terms of inches, I don't need to convert any units. I simply write 1.5 for m. So, when we're all done, our equation becomes d equals 1.5 t plus 96. And that's the equation for this function. Again, you can see the 1.5 is playing the role of the m. That's the slope. That's the rate of change. Here's the 96. This is playing the role of the b. This is the initial depth, or the present depth. It would also be the vertical intercept when we draw our graph. And that's the next step. So let's make some axes. Here's t. Here's d. I'm going to declare this tick mark to be 96 inches. This will be 97, 98, and 99. Here's 1 day, 2 days, 3 days out. So initially, the depth of the river is 8 feet, or 96 inches. If I go out 1 day, the height or the depth of the river increases by 1.5 inches. So I go up 1.5. That would bring me to 97.5 inches. If I go out yet another day, the depth of the river will grow another 1.5 inches, bringing us to 99 inches. So you can see the linear trend. The slope of this line is the 1.5. It's the same as the rate, and the 96 here, that's the B. That's the same as the initial depth of the river. Now let's go ahead and look at example 8.3. So here we are. The graph of a linear function is shown below. The letters W and C represent the independent and the dependent variables. So you can see from the graph, W is the letter that represents the horizontal axis, so it's representing the input. C represents the vertical axis, so it's representing the output. Let's look at part A. Go ahead and determine the C-intercept. Well, when we're talking about a C-intercept, we're asking, where does the graph intersect the C-axis? Well, if we look at the graph, we can see that it intersects the C-axis at C equals 6. So that is the C-intercept. C equals 6. Now let's look at part B. Determine the slope of the line. Remember, the slope is always the change in the output divided by the change in the input. C represents the output, so this is the change in C, which is the change in the output. This is the change in W, which is the same as the change in the input. Let's go ahead and look back up at the graph. So let's see. If we look at this point here and this point here on the line, notice that in order to get from one point to the other, we had to go over 2 places and down 1. If we go over 2 places, that means that we have changed the value of W by 2. We've increased the value of W by 2. If we drop 1 unit, that means we've decreased the value of C by 1 unit. So the change is a -1. So the slope of the line, which is the ratio of the change in C to the change in W, would be a ratio of -1 over 2. That's the slope of this line, -1/2. And again, what this says is that every time you increase W by 2 units, the value of C drops by 1. And that's consistent with what you see on the graph. If I increase W by 2, C decreases by 1. If I increase W by 2 again, C decreases by 1. Increase W by 2, C decreases by 1. That fact is what this ratio is conveying. Now let's look at part C. Determine the equation of this linear function. Well, because it's a linear function, it would have to have this basic form. Every linear function has this form. So for us, y, the output, is being played by the letter C in this case. C is our output variable. X is being played by W in this case. W is our input variable. The slope, or the rate of change, m, we just calculated it to be -1/2. And b, this is the vertical intercept, that's the same thing as the c-intercept in this case, and that we calculated to be 6. So when we're all done, the equation we arrive at is c equals -1/2 w plus 6. And this would normally be written as 6 minus 1/2 w, or 6 minus w over 2. So that's the equation for this function. Now let's have a look at part D. Determine the w-intercept. So in other words, we want to know, where does the graph intersect the w-axis? We don't see it in this picture, but you can tell that if we continued the graph further down, that eventually somewhere, maybe about out here, it will intersect the w-axis. And our goal is to figure out, where does that happen? What is the value of w that will cause the graph to hit the w-axis? Well, recall how you find a w-intercept. If we want to know where does the graph hit this axis, we'll notice that when it is hitting this axis, the value of c will be 0. So you set the other variable, c in this case, equal to 0. So if we go back to our equation and we set c to 0, we get 0 equals 6 minus w over 2, and we need to solve for w. One thing we can do to solve this equation for w is eliminate the fractions that are involved in this equation. There's a 2 in the denominator. If we multiply both sides of the equation by 2, we should be able to get rid of that denominator. So I take 0, multiply it by 2, and I multiply the right side by 2. On the left side, we still have 0. Now I use the distributive property on the right-hand side. 2 times 6 is 12. Minus, now I take the 2 and I multiply it by w over 2, and I get 12 minus, and notice this 2, that's like 2 over 1, so the 2's cancel, and I'm left with w. So the resulting equation is 0 equals 12 minus w, and you can see from here that w must equal 12. So our w-intercept is w equals 12. Does that make sense if we go back and look at our graph? If we go over and look at our w-axis, 12 would be right about here. Does it seem possible that the graph would intersect the w-axis right out here at 12? I think so, because if the graph continued this way, it would meet the axis somewhere out here. Okay, let's go ahead and look at example 8.4. For each of the linear functions below, a brief description of the independent and dependent variables is given. Determine the rate of change, or the slope, and the vertical intercept, and then interpret the rate of change and the vertical intercept in the specified context. Let's look at part A. In this case, the linear function is v equals 0.005p, where p represents the pounds of garbage collected and v represents the required landfill space to store the garbage in cubic yards. So first of all, let's look at the equation that was given. V equals 0.005p, and let's compare that to the basic equation for a linear function, mx plus b. Well, you can see that V is playing the role of Y, the 0.005 is playing the role of M, the P is X, and if I add a 0, then you can see that B is 0 in this case. So M is 0.005, that's the rate of change, or the slope, and B is 0, that's our vertical intercept. So the last thing we're being asked to do is to interpret the rate of change and the vertical intercept in the context that's specified. One thing that you can do to help you interpret what numbers like these are telling you about a particular context, about a particular problem, is start by sketching a graph. So even though this problem doesn't ask us to sketch a graph, I think you'll find it easier to understand the meaning of these two numbers if you look at a graph first. So we'll make some axes. P is our input variable, V is our output variable. In this case, P represents pounds of garbage and V represents landfill space given in cubic yards. Now, if we were sketching a graph of this, we could start at 0 because B is 0. B is our vertical intercept, so we're starting at 0. And let's see here, I'm going to mark off, this is 1 pound, 2 pounds, 3 pounds. And on the vertical axis, I'm going to go up in steps of 0.005. So this is 0.005. This will be 0.010, and this will be 0.015 right there. So I'm going up in steps of 0.005. So now let's use our slope. Our slope is 0.005, and what that means is every time we go 1 unit over to the right, we climb 0.005 units. If I go over another unit to the right, I climb 0.005 units. Again, if I go another unit to the right, I climb 0.005 units. And that gives me a line with a slope of 0.005. Now we can begin to interpret what the numbers M and B represent in the context of this problem. B equals 0, that told us where we were starting from. Well, let's think about this in the context of garbage and landfill space. This point right here tells us that if no garbage has been collected, in other words, 0 pounds of garbage have been collected, then 0 cubic yards of landfill space would be required. That's the interpretation of our vertical intercept. What does our slope represent in this case? Well, our slope told us that every time we increase our p-value by 1, we climb 0.005. Every time we go 1 unit to the right, we climb by 0.005. In other words, every time we increase the amount of garbage by 1 pound, the amount of landfill space required to store it increases by 0.005 cubic yards. So, an interpretation of our slope, or our M value, would be the following. So each additional pound of garbage requires 0.005 cubic yards of landfill space. So that would be an interpretation of our slope or our rate of change in this context. Now let's do the same thing for part B. Why don't you go ahead and pause the recording at this time and try and work part B on your own first. You can take the same approach we used in part A and then continue playing the recording to see this problem fully worked out. Okay, let's go ahead and look at part B. We have the equation C equals, I'm going to write this a little differently. I'm going to write the 0.2 u first and then plus 14. And we compare this with y equals mx plus b. So you can see from comparing these that our equation here has the same format as this one, and you can see that the m is the 0.2 and the b is the 14. So m is 0.2, b is 14. So next we want to graph this line. We have the letter U on our horizontal axis and C on our vertical. C is cost in thousands of dollars, and U is the number of units that have been manufactured. And let's mark some tick marks on here. This will be 1 unit, 2 units, 3 units. And I'm going to declare this to be 14, and I'm going to go up in steps of 0.2. So the next tick mark, let's say that's 14.2, the next one is 14.4, and the next one is 14.6. Now let's go ahead and draw this graph. So our B is 14, that's our vertical intercept. So we're starting at 14. Our slope is 0.2. That means every time we go 1 unit to the right, we climb 0.2 units. That's why I went up in steps of 0.2. If I go 1 more unit to the right, I climb again 0.2. If I go 1 more to the right by 1, I climb 0.2. And so we arrive at this linear trend. Next we want to interpret the m and the b values in the context of this problem. Let's start with the b value of 14. What does that mean in this problem? Well, the 14 told us where we were starting from. Remember, the b value is like our initial amount. In this case, we'd be talking about our initial cost in thousands of dollars. At this point, u is equal to 0. In other words, we haven't produced any units yet. So no units have been produced, yet there is a cost of $14,000. Remember that when you're producing something for sale, it costs money even before you start producing your items. So this $14,000, maybe you could think of it as startup costs. So now we've interpreted the b value. Next we interpret our slope. So our slope tells us that every time we go 1 unit to the right, we climb by 0.2. Go 1 unit to the right again, climb by 0.2. So every time we produce an extra unit of our item we're manufacturing, the cost grows by $2,200. Well, $2,000, what is that? That's the same thing as $200. So what we're saying is that every time we produce another unit of this item we're selling, the cost increases by $200. So really the slope is telling us the cost to produce each unit. Let's write this up. So the cost to produce each unit is $200.